Well, it's good to be here, but since the time is short, I'm going to get into this very quickly. I'll just say what you might have already guessed. We haven't solved the problem of core collapse mechanism. I know you're surprised. I am too, after how many years? Yeah, that's the summary. Nevertheless, I want to convince you that there's been a lot of progress in the field. And some of the progress is actually connected with the fact that instead of a few groups doing credible work, there are almost 10. Well, I didn't parse it that carefully. Some were doing credible, some were doing incredible, exactly. I'm not going to summarize all that work. I thought I was going to take as my charge, in fact, to be a little bit critical. And so what I'm going to do is to try to communicate as best I understand it.
Just want to make sure.
As best I understand it, the current status, and to give you some caveats, because this is unfortunately a numerical problem. I do not like numerical work. But the unfortunate thing is that it's required. Nature does this effortlessly, and we have to use computers to actually simulate the complications that seem to be central to the mechanism. And so one of the things we have to be able to explain is this. This is a nice distribution with X-ray data of the iron and the silicon in Cas A. And the basic point here is that this is not spherically distributed. That there are clumps, tendrils, fingers, and bubbles in these structures that we have to explain. And these structures basically bespeak those distributions that we have to reproduce. And so we can't do spherical models. That's a solved problem, basically. We can do radiation hydrodynamics in spherical symmetry. We have the tools, we think we have the physics. Unfortunately, that's not been adequate. Now, there are also new data, of course, on the distribution. In Cas A, we have the new star data, the titanium-44 distribution. And what's indicated here is the same sort of thing, that you have low-order modes, a low-order L mode distribution of the ejecta. This is the titanium-4 distribution. And you see you have L equals 5 to 10 to 2, this sort of thing, but not L equals 50 or L equals 100. It's not small-scale structures. Now, this is the distribution of iron. This is the distribution of titanium in Cas A. And you may notice, and again, there's some complication here because it really reflects the overlap of iron with the reverse shock. But you might notice that where there is iron, there isn't titanium, and vice versa. This may be telling us something about the nature of what's being ejected, the entropies, in fact, and the density, distribution, and angle, to give you alpha-rich freeze-out. Now, this is, of course, what you might expect if you do the simulations. This is just an example of a very simple simulation, simple in that the neutrino transfer is very simple. We just wanted to show the basic distributions of the bubbles that are and the structures that are produced. And you can see that these do look a little bit like, and this is generic, I didn't just cherry pick this. These do look a little bit like the distributions that I showed just earlier. The basic mechanisms that have been discussed, and I don't really need to go through this in detail for this audience, are the direct mechanism, spherical mechanism, and that hydrodynamic mechanism. That does not work. We think it doesn't work from a theoretical perspective. We do not have real data that indicates it does not work. But the physics is pretty compelling. However, there are some progenitor structures where a wind model works, where in spherical symmetry, the neutrino heating of the atmosphere, when there's very little density on the outside and the protoneutron star is more or less isolated from the beginning, is adequate to give you an explosion. But that explosion is generically 10 to the 50 ergs, a tenth of a beta, and we can't get that mechanism to give us the generic supernova of core collapse character. People for many years, and I'm going to show a little bit of this too, have been doing 2D simulations, 2D radiation hydro. For many years, this was actually the state of the art, and I'm going to show you a few new things in 3D, and there are many groups now that are starting to do this, but it's very computational intensive, very slow. The goal is to do 3D and be able to make mistakes every year. So far, we haven't been able to do that. We've made a lot of mistakes, but we haven't been able to do them in 3D. Now, that might seem facetious, but what I really mean is that they've been so expensive that you exhaust your allocation in the year doing one calculation. And if you were wrong, or if you just didn't have the chance to do what theorists should do, which is to explore, then you really haven't made a lot of progress. So the goal in the future is to be able to do these 3D simulations fast, so you can make one or two mistakes. And I'm going to hope to motivate that we actually are almost in that era. Now, we've been talking about GRBs recently, and so I did want to make a connection, so I added a little bit about this. If you have rapid rotation in the cores of these things, it's really hard to suppress a magnetically driven jet explosion. But I don't think this is generic. I think this is hypernovae. And I'm going to show something and also maybe make a connection with what was talked about earlier. But we basically have to do the 3D. And what happens in the 3D is different from in 2D. So that's also one of the themes I'm going to be talking about. So the important ingredients and important physics that you have to put into this, and it isn't just a numerical problem. It may not be clear from some of the literature, but a few of us have to think every once in a while. I hope it'll be clear after my talk that some of us have been. So you have to do multi-D hydrodynamics and radiation hydrodynamics. And right now, that's a 7-dimensional problem. You have to do it in phase space and in time. So it's 3 plus 3 plus 1. Nobody's done that. Okay, so you make approximations for the specific intensity distribution. You might use moments and a moment closure, et cetera. We're working towards the capacity to do in 3D, 3 spatial dimensions, that type of a calculation, but nobody is doing that now. Okay? We've done that in 2D, and a calculation that took 1 month normally took 7 months when you tried to do it this way and at lower resolution. Instabilities are rather crucial. In fact, I'll show a difference between 1D and a multi-D calculation, and the stalled shock, and again, this is a context in which we're trying to revive a stalled shock, if this mechanism is at all true, the neutrino-driven mechanism. There are instabilities, and the difference between the stalled shock radius in the 1D case and the 3D case is crucial. It's easier to explode in multi-D because that stalled shock is at much larger radius, shallower in the potential well, with a larger region that can absorb the neutrinos. The neutrino processes are important too. I once thought that they weren't crucial because when you do 1D simulations and you change things a lot, things don't change too much. But as we go up in dimension and that stalled shock becomes a little bit less stalled, then some of the details make a difference. General relativity, and there are approximations being made here, would be important, and it's only in the last few years that that importance has come to the fore. And rotation may be important too. This is something that has not been well explored. I'm not going to talk any more about this, but if you invite me back 6 months, I might. Okay. Now, in 1D, as I said, these things can explode. This is just an old calculation. This is 5,000 kilometer radius here. That's shock wave. Those are the velocity vectors. You'll notice it was almost an immediate explosion, and it's spherically distributed. But this is the case for only one small set of progenitors where the density profiles are very steep on the outside. That's that wind explosion. And this was just a little bit less than 10 to the 50 ergs. Okay. So let's get to the MHD. And one of the reasons I wanted to mention it to this audience is that if you do have a collapsar model, there's a delay to the black hole formation. And during that time, you're going to generate an explosion that's going to be baryon loaded along the axes. And so the collapsar model should have a precursor, which is a non-relativistic jet that might have more energy than the GRB itself. The GRB would be collimated, has to be relativistic, but it could be, a precursor could be an energetic subrelativistic jet. And it's really hard to suppress those in the second or 2 or 3 where you're waiting to form a black hole. So that people should keep that in mind. That in fact, something like this might precede a gamma ray burst. And maybe the more energetic component in the massive star, if it's the collapsar model. It also has to precede the magnetar model, because you're forming a neutron star. And in fact, it starts out with the magnetar with 10 to the 15 Gauss fields, and here you generate them. You get up to that phase. So these things are connected. These are radiation magnetohydrodynamic simulations, but in 2.5D with axisymmetry. And this is the type of thing that happens where color is the shocked material. There's a stalled shock, the bane of our existence, but the B fields are going up at prodigious rates, and then you just generate bipolar shocks. And again, this is just representative B fields. With this sort of thing in rapid rotation, you can get to 10 to the 52 ergs. The neutrino mechanism, back of the envelope or in detail, has never been shown to be able to get up to those energies. So MHD may be crucial for the most energetic of the explosions that we know and love. There was a nice calculation in 3D of this sort of thing. They got a power density which was spread out a little bit more because of kink instabilities, but it's straightened out again, and you have the same power. So a little wider angle, but you get basically the same sort of thing. This is the multi-D, 1D comparison I just wanted to show. These are a variety of progenitors. In 1D, where this is the shock radius, 100 kilometers, 200 kilometers, 300 kilometers, and you see it goes up to this radius here. This is a non-relativistic calculation, by the way. And then it just sort of settles down. When you do multi-D and you have various perturbations or something, you always get to much larger radii, generally about 50-kilometer differences. And that makes a difference in this context because it's shallower in the potential well. When you accrete the silicon-oxygen interface, and those are always in the progenitor models, however rough they might be, the density drops off, and you get a jump. And it's possible that some models or some objects actually will explode when they accrete these shelves. So one of the themes is the shelf that might be accreted at the silicon-oxygen interface. Another is perturbations. Recently, people have shown that with significant perturbations in the progenitor of the explosion, in the massive star core, you might be able to kick it a little bit more and put more kinetic energy early on inside the so-called gain region, which is the mantle that will explode. You always leave behind the neutron star or a black hole. This is an example of such simulations using a new code I'll get back to, and this has relativity in it. What this is a standard model, blue. Standard is just, and this was done in 2D, in fact, and you see that oscillation here, the shock goes up, nothing much happens. The point here is at high resolution, you have green curve there. There are differences, but the resolution dependence of that behavior has been captured. Now, it's not in detail, but in fact, these calculations are resolved in this sense. Now, you just do the same calculations, but perturbed by accreting significantly perturbed material, and these perturbations represent, for example, mixing length turbulent velocities, or 5 times that. And these are the types of responses you get. Remember, the position of the shock is rather crucial. And with significant perturbations, you can get a difference between this curve and this curve. This is just as an example of what's possible with significant perturbations on infall. So that's, again, part of the theme. There's doing the calculations at higher resolution, there is the accretion of the shelf, and there is the perturbations. This is just to show a recent simulation, and the color map was very poorly chosen because this is something's happening right now. There's bounce, the shock, and this didn't have any perturbations on it. But you get numerical perturbations on the grid level or due to the truncation, but you'll always get something. This actually waited a long time. It actually survived without being unstable, and again, this is actually moving. It survived without being unstable for about 30 E-foldings, which is pretty good numerically, but it was still, the reason for showing this is just the basic character of these 2D simulations. You get these oscillations, and I'm going to argue that these oscillations in 2D are rather artificial. This is what you get in 2D, but these oscillations are mostly neutrino-driven, and there's the so-called standing accretion shock instability, which I think is subdominant. But the reason for showing this is the highest resolution simulation ever performed. This is 512 angle, 100, we've done one at 1700 in radius, 40 energy groups. And we find that resolution like this might be necessary. That's why you need the numerical arts, because that could be very expensive and it goes as a power law. Now, there are groups around in the world that are seeing explosions. Almost all these explosions are in 2D, and those explosions are generally subenergetic. So you can get explosions, but can you get 10 to the 51 ergs generically? That is really the goal. And can you get it credibly? The Oak Ridge team is doing a great work, but this is their example comparison. This is 1D versus 2D, and in 1D, no explosion, but in 2D, they had explosions. But they're getting explosions for these particular models at almost exactly the same time. Whereas the group Suma et al. From Max Planck is looking at the same models. These aren't the same models, but if you look at the plots, I couldn't find a good plot that I had readily at hand. But if you look at those models, they're all exploding at different times when they explode. And these times are much, much later than the 100 milliseconds or 200 milliseconds or something like that, depending on where you define it, of the explosions of the other group. And our recent simulations do things like this, where you have 150, this is with relativity, et cetera. It also has some interesting art in the neutrino matter cross-sections, and this isn't published yet. But generally, we get explosions here for this range as well, and more or less similar to the SUMA stuff, although a little bit more tight. So it's possible to get explosions, but now we have to, because things are more sensitive at higher dimensions and are resolution dependent, we have to really know what we're doing, because it's now easy to get explosions. But we haven't been able to explain the energies either. And so there are differences between the groups. This is just some examples. This is some of our older calculations. These are some newer calculations. This is representative of Bernhardt's calculations. When they do get explosions, you get an abrupt jump. This is almost abrupt, but generally with these types of simulations, you get an abrupt jump because the explosion can be shown to be a dual cusp instability. It's a bifurcation. And you can show almost analytically, it's a little bit messy, that in fact this is just from bifurcation theory that you reach a critical condition. Now that's easy to say, you have to do it numerically, but there's an interesting aspect of that. Okay. So I'm going to start talking about a few problems. The progenitor models that we inherit are hard-won. There's a lot of physics that are involved. Stan has done some, Ken has done some. We have a whole community that's doing these. But that's what we inherit. And those profiles, those density profiles, map directly into the outcomes. Here's just examples. That's the Chandrasekhar mass, a density of 10 to the 10, 10 to the 8, et cetera. And these density profiles are very different. This black curve is the one that gives us the wind-driven model, but these others don't. And so this is going to give you a different accretion regime for that standing accretion shock that we're trying to re-energize into an explosion, and it makes all the difference. It's also the case that generally people ignore this. This is the binding energy in the progenitor models exterior to 1 solar mass, 2 solar masses, 3 solar masses. If you want to leave behind a neutron star of 1.5 solar masses baryonic, then you have to eject the material. Go to 1.5, go to the progenitor. You have to eject all that energy. And for a number of progenitors in the literature, that energy is 10 to the 51 ergs. That means if your explosion is 10 to the 51 ergs, you get nothing at infinity. So we have to get 2 times 10 to the 51 to get 10 to the 51 for many, many models. That may be a reason that some of these models don't explode. Much of the mass function is at lower masses, and the binding energies are generally smaller. But this is an important, crucial aspect that people should keep in mind. When people quote energies, they don't always quote it with this correction, and they almost never simulate all the way. So there are a number of problems with extant models. I'm going to go through some of these. There's a method that's being used for the transport, which is one-dimensional transport calculations in a 3D or 2D simulation. It's called ray by ray. It isn't getting the specific intensity distributions at all. It's doing 1D along the temperature density profile in that direction with a few corrections, and then doing it differently in this direction, et cetera. When you do these calculations in 2D, the pole to equator contrast is much larger than it should be. It's frequently the case that calculations are done excising the cores. So it might be multi-D on the outside, but it's 1D in the center. That way you can't get kicks, and if there's some interesting turbulence in the interior, you've ignored it. There are many other examples of problems here. I think the progenitor structures are key. Now let's get to the 2 instabilities in this context, the SASSI and the neutrino-driven convection. On the left-hand side is a SASSI simulation where this shock is stalled. And here, all I do is turn on neutrinos. The shock by itself, this standing accretion shock instability, does oscillate, et cetera, but it doesn't oscillate with the same vigor. If you don't have neutrinos driving it, then there's no entropy generation. And here, the red and yellow colors are entropy generation. And so there can be a qualitative difference. Notice how the pole equator contrast is so much larger here, and the shock radii are larger, and this particular simulation was made to explode because the luminosities were high. So this is a big difference. It's this that we're looking for. And you can do this a numerical study where this is the dipole component of the shock radius. As you ramp up the neutrino luminosity, you get Small values, then it jumps up. It's only when you have these large luminosities that the neutrinos can drive an explosion that gives you enough energy to drive the explosion, and that's when neutrino-driven convection dominates. The instability is called the SASE, is subdominant. You can also do the Fourier analysis, and you can see what the dominant frequencies are. And for low luminosities, you get this SASE tone at about 50 hertz for this set of calculations. You ramp up the luminosity, that goes away, is not dominated, and you get basically convection. So when the neutrinos drive explosions, then it's the neutrino-driven convection. And the SASE is really subdominant. I emphasize this because this hasn't really taken hold. It's there, but with the neutrinos on and operating, then it's really not an important effect. When you do transport, even when you have a background of complicated hydrodynamics, the transport vectors, the flux vectors, these are just representative, basically stay almost radial. They dance around a little bit. That's because at one particular point, radiation is produced by fluxes from, or specific intensity rays from many different directions, so it smooths itself out. The ray-by-ray technique doesn't do that. So here's a comparison. If you do the calculation, the reason many people have been using this technique is that it's simpler and it parallelizes well. And there haven't been too many codes that can actually do both. And so our recent code, Fornax, it doesn't stand for anything, okay, actually can do both. And so this is a comparison where all you do is do the calculation multi-D and then use this ray-by-ray approach. And look at the red curve. That's the maximum shock radius in a 2D simulation, 200 kilometers there. And you get it sort of, then it goes up like this. Here, it went up much more early and more significantly. Here, in this calculation with this different progenitor, the multi-D actually didn't do much, but the ray-by-ray exploded. And so you get things like this. This is without the ray-by-ray for this type of simulation. Now, this isn't the final word in our simulations with multi-D. This is just comparison between the two. You get a lot of bouncing around, et cetera, but nothing much happened. In this set of models, just using ray-by-ray, and that's a switch in the code. And the reason for this is that along the axis, the transport is correlated with the axis behavior. And so you get it in a phase. It phases itself. So when you get significant anisotropies, pole equator anisotropies, you amplify the problems with the ray-by-ray approach. The other thing I want to emphasize is 2D and 3D are different. We keep doing 2D because they're cheaper, for the reasons I said. So we really need to get to 3D. These are simulations where this is 2D, the same simulation done in 3D, and you don't see the axis effect. Okay? You also see small-scale structure. There's a nice little comparison that Sean Couch has made. This is the 2D simulation, if you're honest, and this is the 3D simulation. There's a difference. Now, when you do a 3D simulation, this has no preferred axis, even though there's a grid that has a preferred axis. And you can see the type of small-scale structure, not a lot of large-scale structure. But when this does explode, it chooses a direction. And what happens is that in 3D, an explosion is an L equals 0 instability. The L equals 1 dipolar mode starts to become unstable at about the same time. So when it explodes, it frequently explodes in a dipolar fashion. And you get bubbles like this, bubbles hitting the shock, for example. And when it does explode, it'll explode out in some direction. And that'll naturally give you a recoil and kicks. It'll naturally give you a preferred direction, but it'll choose it. This is without rotation. And I'll skip that. So, in order to try to do what I introduced people to in the beginning, to do 3D simulations often enough, we had to put together a whole new code from scratch, and this is the Fornax code. I'm not going to show a lot of results right now, but I want to motivate what the reason is. The transport that has been done in the past has been implicit. This is for the cognoscenti. You have to actually, when you do domain decomposition, you have to communicate all through the computational domain to get the solution at any particular point. That puts a real strain on the message passing and the communication. That's required for doing things implicitly. But it turns out in this problem you could do everything explicitly, because the speed of sound and the speed of light are close in the center. We're already limited by the speed of sound in the center by the Courant condition. Again, this is technical stuff, but I just want to give the basics. And so we can actually do the calculations explicitly without the massive communication overhead. And the net result is something like this. These are scaling relations. Our old code here, which was tried and true, actually could scale up to maybe 110,000 cores. The new code, without any effort at all, scales up to 200,000 cores, and that difference right there is the efficiency difference. 1 calculation per year, 5 calculations, 10 calculations per year. And it's just because we can do it explicitly. So there are many advantages to this new approach, which is what I would advocate. We're already limited by the Courant condition in the center by hydro. But we can do the transport now. It's even more accurate with doing this explicit method. And there's a lot to say. We can actually do the calculations to the center because we're using a so-called dendritic grid, which is basically static mesh refinement. So let me just summarize. The SASE is not really a mechanism. It's really there, but it's important that the neutrinos are much more important if it's neutrino-driven. The ray-by-ray approach, which people are starting to recognize, may be problematic. It may be less problematic in 3D, in fact, maybe ironically, but the 2D simulations are much worse. 3D is different from 2D. GR is probably important, but the progenitor structures are crucial. What those are will determine, when we have the right physics, what happens. And because this is a turbulent medium, the results are going to be stochastic. The same progenitors are going to give different results. And so we have to understand it statistically, which is a pain. It's a pain for us. So not only the progenitor is important, but when you get to multi-D, the details of the input physics are starting to become important. But I'm optimistic now that there are tools and techniques and many groups that don't agree, so that it's a productive ferment on everything, that we are actually on the cusp of being able to solve this problem in the next few years. If we don't solve it this way, then there's another mechanism. It's looking as though this is looking pretty good. We understand how to get explosions. We want to know whether nature has obliged us with this mechanism. And at that, I'll stop. Thank you very much for your patience.
So with the best current simulations, what is your expectation for LIGO in terms of detecting a gravitational wave signal from supernovae?
Now, Bernhardt may be talking about that on Wednesday, but I'll chime in a little bit. It's amazing what the technology of LIGO. I mean, we've all been overwhelmed by what they've been able to do. They've been interested in supernovae, and every one of our simulations, for every one of our simulations, we calculate the gravitational wave signatures. Those signatures, I believe, are strong enough to be significantly above at 10 kiloparsecs, the advanced LIGO sensitivity, at around 100 to 200 hertz. There's going to be power over that whole range from 1 hertz, in fact, up to a kilohertz. It's a matter of picking out a signal that can't be templated. But there are signatures having to do with rotation, having to do with convection, these sorts of things that, in principle, with good signal and noise, you can actually extract. In our galaxy. There's only one possible mechanism that you can see maybe out to Andromeda, but I think it's not very likely. So I'll say it's in our galaxy. Yes, there is a real potential, and I'll leave it to Bernhardt to talk on Wednesday.
Yeah, a couple comments and a question. One, I think the average supernova energy is more like 0.6 beta, and not 1. And the number of stars from 8 to 11 solar masses could potentially explain about half of the supernovae we see. Most people are able to blow those up. The titanium 40.
They don't blow them up with sufficient energy.
To blow them up with up to 0.3 beta, which is
that's
not,
2D simulations.
There's going to need to be something else. I'm just saying it's not all quite so hopeless as you sometimes paint. Titanium 44 is a trace nucleus. You cannot make it without making nickel 56. But you could make smaller amounts of nickel 56 and still make the titanium, but only by maybe a factor of 2. Question. You mentioned the jet that you calculate that might precede a gamma ray burst. The jet moves with some speed. The gamma ray burst moves faster.
Right.
Won't it overtake it?
It depends on the accretion rate. I think it would overtake it within something like a few seconds. I'm not debating that, but by that time you could deposit a fair amount of energy, and that could give you the supernova explosion, the type 1C.
It'll make it easier, but it won't give you a precursor.
It will be broader, and it might be more energetic. But it's going to be there.
Thank you. Thank you, Adam. I have one question, because a lot of the results that you showed on, let's say, the ray-by-ray approximation, the standing accretion, shock instability, resolution dependence, and so forth, that was from 2D simulations. So how would you think, would that picture change perhaps in 3D, also considering some of the recent simulations that have been out in the market, where we at least see some role of the SASE in providing pre-shock expansion before the explosion sets in, and also the results of Fernandez 2015, who claimed that the threshold luminosity in the SASE-driven regime could actually be lower than for the convective regime.
Yeah. Concerning the latter, I'm not so sure those sort of semi-analytic calculations or simple without neutrino transfer calculations really are informative of the role of the SASE. I'm not saying that it's not there. It's just if you're going to deposit that amount of power behind the shock, you're going to drive significant neutrino-driven convection. And it's going to overwhelm the SASE. The SASE stability analysis has not been done with neutrinos. And so when you combine the two, you have to do an instability analysis to get the dispersion relations, et cetera, with the two together.
Yes, but I mean, we saw it developing quite vigorously.
Right. And let me answer the first part. I think in 3D, without rotation, that the ray-by-ray is better. I think you can get away with it a little bit better, but I'll mention to the audience that, again, in 3D, it's been more difficult to get explosions. So a lot of what you've seen in the literature is the 2D simulations. There are a few 3D simulations that show explosions, but if they do, they explode late or with some changes of physics, et cetera. I think nature is making it very difficult